Good day, all colleagues and friends. We're very pleased to meet everyone in our regular meeting dedicated to education in Russia in the field of non-power nuclear energy. We organize this meeting every year and collect students who are interested in Russian education in this field. Today we have a workshop about education in best universities in Russia. It's a MEPhI and Tomsk Polytechnic University. And we have two speakers that join us to present the programs in radiation technologies in environment protection and nuclear education and career. So I would love to give a floor to Professor Tatiana Melnikova, the representative of MEPhI University, and she will discuss with us about radiation technologies and environment protection. Please.
Oh, one moment, please. So I hope you see my presentation. So one moment, please. So today we discuss the radiation technologies in environmental protection. As you see that radiation technologies have long and quietly become a part of our everyday life, at home, on the way to work, working in the office, or even while on vacation, we, without knowing it ourselves, use what was created with their help. The main quality of radiation technologies is very versatility, the possibility of application in almost all areas of development and spheres of human existence. Often we don't even know that all this possibility appeared thanks to the limitless power of the peaceful atom. So radiation technologies studies, develops, and improves methods, techniques, and devices that use ionizing radiation. Despite the fact that radiation technology is relatively new field in the scientific and industrial sectors, the pace of its use throughout the world is growing every year. The main directions of radiation technologies are presented on the slides, indicating the expansion of the scope of application of radiation exposure and its introduction into the field of human activity. There are no clear boundaries. The considered directions of radiation technology. Common of them are the problems of design and manufacturing sources of ionizing radiation and radiation installations, technological dosimetry of radiation used, and of course, environmental safety, excuse me. So currently, research and technological developments in this area of environmental protection and radiation technology are carried out in following main areas, such as radiation treatment of natural water, radiation treatment of domestic, industrial, and agriculture wastewater, radiation treatment of exhaust gases, and the last, radiation treatment of solid waste. So, for radiation treatment of various objects, Installation with the following types of ionizing radiation are used. The first, electron radiation with energy no more than 10 mega electron volt. Then gamma radiation of radioisotope cobalt-60. Gamma radiation of radioisotope cesium-137. And the last, bremsstrahlung X-rays radiation generated by electron accelerators with an energy of no more than 5 mega electron volt. The choice of the upper limit, upper energy limit for electrons and X-rays is due to the fact that induced radioactivity doesn't appear at these energies. The energy of gamma rays can't be higher than 5 mega electron volt, since this radiation occurs when an excited nucleus returns to a low energy state. Of course, all types of radiation have certain advantages and disadvantages. But nowadays, installation with radionuclide radiation sources and electron accelerators are widespread. Why? Because they most fully meet the listed radiation safety conditions during their operation. So let's look at real examples for application of radiation technologies. You know that natural water from rivers, lakes, other water bodies, yes, intended to supply the population may be contaminated with harmful impurities and contain pathogenic microorganisms and parasites. Often the concentration of such impurities and the level of concentration are low. So relatively low doses are required for radiation treatment of water. Doses of 1 kilogram are sufficient for purification and disinfection of natural water. In particular, for the decomposition of organic compounds that cause odor, color, etc. One of the important tasks of radiation technology is the purification of natural water from the toxic and cancerogenic chlorine-containing organic substance. This substance enters water from a polluted environment and are formed during the chlorination of water containing certain organic compounds. Irradiation of water contaminated with chlorine-containing organic substance leads to their decomposition. Small amounts of this substance can decompose at relatively small dose of 1 kilogram. The use of radiation methods in this case of such system is promising. So, however, there are problems. For example, during radiolysis of chlorinated aromatic compounds, dechlorination may be accompanied by the formation of other toxic substances. For example, during the radiolysis of chlorbenzene solutions, phenolic compounds appear. In addition, there is noticeable dependence of the yield of decomposition products on the dose rate. Irradiation of contaminated water in combination with ozonation causes a synergetic effect. Thus, ozonation of water, irradiated water, ozonation of the water contaminated with the, for example, trichloroethylene and tetrachloroethylene almost completely eliminates the influence of dose rate in dilute solution, and also protects irradiated water from the reappearance of microorganisms and parasites when transported in through pipelines. Next. Household wastewater can be used for technical purposes after biological and then radiation treatment. This was confirmed by South Korean specialists who studied the features of such treatment using a small pilot plant with cobalt gamma radiation sources. For radiation treatment of domestic wastewater after its biological treatment, dose of 0.4 kilogram to several kilograms are required. It is recommended to use radiation-treated household wastewater for technical purpose. Industrial wastewater differs from contaminated natural water in the variety of impurities and their significantly high concentrations. To clear such wastewater, large doses are required, 10 of kilograms or more. As a result, combined purification methods are being developed in which radiation treatment is used in combination with conventional methods such as chemical, biological, thermal, then flotation, etc. And when using combined methods, a synergetic effect is often observed. So, when wastewater settles, sediments are formed, and these sediments consist of insoluble solid particles and water. During biological treatment, a different type of sludge occurs at the aeration stage, called excess activated stage. A significant part of them are microorganisms. Sediments can be used as fertilizers and animal feed additives. However, they contain microorganisms, parasites, and toxic substances, as a result of which they must be disinfected and rendered harmless. A commercial plant with radionuclide radiation sources was operated for 20 years near Munich, it is Germany, was distinguished in 1993 due to the fact that Germany banned to use sewage sludge, both irradiated and no-irradiated, as fertilizer due to its content heavy metals. Interest in the area of radiation technology has continued and is likely to continue in a number of countries with agricultural areas that don't have a heavy metal problem. Many researchers have shown that this disinfection and purification sewage sludge can be realized using radiation methods. In this area of radiation technology, installation with sources of gamma radiation and electron accelerators are used. The problem of the disinfection before use can be successfully solved using radiation method. Disinfection is achieved at doses from 2 to 10 kilogray. Next, in the USA, Canada, Russia, and other countries, a relatively large amount of used transformer and hydraulic oils contaminated with toxic polychlorinated biphenyls has accumulated. Polychlorinated biphenyls belong to known radioactive industrial waste from nuclear power plants and are included in the list of persistent organic pollutants defined by the Stockholm Convention in 2001. This slide presents a table with results of decomposition of mixture of polychlorinated biphenyls when irradiated with the same doses, but the different energies of accelerated electrons, 1.5 and 2.5 mega electron volt. Based on the results of the table, biphenyls, when irradiated at dose of 180 and 250 kilogray, are destroyed to concentrations that are beyond the detection limit of the device. According to the slide, the efficiency of such treatment reaches 99%. However, this method has so far been studied only in laboratory conditions. Pilot installation have already been developed and are operating for radiation disinfection of medical waste. Apparently, more widespread use of this method can be expected in the near future. Radiation sterilization is a physical process involving the radiation of medical devices with ionizing radiation. Products are irradiated in specialized radiation technology installation using the gamma radiation sources of radionuclides such as cobalt-60 and cesium-137, or electron accelerators generating beams of electron or only a beam of electron. So, when performed currently, radiation sterilization is a safe and reliable industrial process. Next problem, radiation treatment of soils contaminated with harmful organic substance was studied. Positive results were obtained, but the doses required for purification are in most cases very, very high. For example, to clear soil contaminated with dioxide by gamma radiation of its aqueous suspension, a dose of 0.8 megagray is required. So, very good result have been obtained with the regeneration of activated carbon using radiation. Despite the fact that large doses of radiation are required, it is economically very profitable to use this method. Nowadays, an area in radiation technology is intensively developing, affecting one of the most important environmental problems. It is the purification of exhaust gases from harmful impurities, such as sulfur dioxide and nitrogen oxides. The use of electron beams is a promising method for purifying these gases. In addition, electronic processing of gases containing sulfur dioxide and nitrogen oxides allows them to be removed simultaneously. Research into the problem under consideration began in the early 70s in Japan. Subsequently, it was shown that addition of ammonia to the irradiated gas causes the formation of powdery product, sterile insect technique. So I repeat information about this method. Yes, this is a very important area of radiation technology. From the one moment, please. One moment, please. So I check my microphones. Important area of radiation technology from the point of view of environmental protection is the sterilization of insects, which are agriculture pests and spreaders of diseases. The developed method includes radiation sterilization of males and their subsequent release into the wild. They obviously can't produce next generation. This leads to decrease and even complete destruction of the corresponding insect population. And of course, this method is widely used. So, in the last slide, the considered examples clearly indicated that development of radiation technology contributes to environmental protection through both indirect and direct contributions. It is developing at a relatively fast pace. Other areas of radiation technology that are indirectly or directly related to environmental protection include radiation sterilization of medical products and device, then radiation purification of gas emissions, wastewater and infectious medical waste, radiation treatment of natural polymers, radiation modification of materials, radiation sterilization of insects, etc. It is hoped that radiation technology will develop at a faster pace in the 21st century. Thank you for your attention.
Thank you very much, Professor Tatiana Melnikova. Very grateful for your presentation with very interesting and useful information about new technologies, technologies of future, and a very important topic about how to protect our environment in future. Thank you very much once again. And I give the floor to Julia Weber, the Dean of International Center of Nuclear Education and Career, the famous Tomsk Polytechnical University. Please welcome Julia. Listen to you.
Thank you very much for giving us this opportunity. I would be happy to share the presentation with you. Just a moment, please. Just a moment. Just a couple of seconds, please. Excuse me, please. Do you see the presentation? Everything is fine. Thank you very much. I'm very happy. Thank you for your feedback. My name is Julia Weber. I represent Tomsk Polytechnic University, which is located in Siberia. This is the center of the Russian Federation. We welcome a lot of international students from different parts of the world. And today I was delegated the right by Dr. Vera, who is the director of our Research and Training Center for International Nuclear Education and Career, to give a lecture for you on non-power applications of nuclear and radiation technologies. First of all, I would be happy to say that speaking about non-power application of nuclear energy, this is the main topic when we talk about the complex usage and implementation of research and testing reactors. First of all, it is important to differentiate between what a nuclear reactor is and what a nuclear research reactor is. If we talk about nuclear reactor, which is used at nuclear power plants, of course, its main purpose is to produce nuclear energy, which later will be used for the production of electrical energy, electricity, the so-called, which we receive daily. If we talk about research reactor, research facility, of course, this is something different. This is a kind of nuclear facility which includes research nuclear reactor or a critical assembly or a subcritical assembly with a complex of structures, systems, components, which is accompanied by the specially well-trained, qualified personnel, and which main purpose, of course, is to use neutrons and ionizing radiation for conducting research. And not only research. And we will be talking today about different applications of nuclear research reactors, which are used for almost everything except for the production of electricity. Of course, in my previous slide, I mentioned ionizing radiation, and we should not be afraid of this term once you hear this. Of course, the term radiation is very broad, includes such things as light and radio waves. In the context we are speaking today, ionizing radiation means a kind of radiation that passes through a metal. It can cause it to become electrically charged or ionized. We talk about electromagnetic radiation, particulate radiation, direct and indirect ionizing radiation. And when at a nuclear research activity, at a nuclear research reactor or facility in general, we would also meet these different types of ionizing radiation, which are accompanied with the emission of alpha particles, beta particles, X-ray, gamma rays, neutron emission, etc. But the proper shielding, the proper radiation protection would help the personnel, you see, not to be exposed to radiation, because special materials are used to counter the radiation exposure, such as, for example, in some cases, this could be even paper, or aluminium, or lead, or concrete. To continue, I would pay your attention to a number of research and testing reactors. their classification. This slide, you would see the main 3 examples of these facilities, such as subcritical stand, which is used now in Greece as an example, critical stand in the Republic of Belarus, and nuclear research reactor, ITT, located in Russia, mainly in our university. Tomsk Polytechnic University is known as the only university which owns its own reactor, the only operating research reactor in Russia. And I will tell some more interesting detail about this work, about this operation, how it is used, different applications, etc. But to continue the topic of research in reactor, of course, it is necessary to present a very short information on the classification. And here on the slide, you would see 4 main criteria. 4 main criteria in accordance with which the nuclear research facilities are distinguished. First of all, this is the purpose. What for is the research reactor is used? It could be used for physical research, for material science research, and of course for isotope production. If we talk about the operating mode of the nuclear research facility, we would classify the reactors as pulse mode, pulsating mode, or long or stationary mode of its operation. If we talk about such criteria as neutron flux density, we would distinguish the research reactors into 3 main categories. 1, low flow, medium flow, high flow of neutrons. If we speak about neutrons, are the moving force of this flux. And the last criterion is neutron flux spectrum. In accordance with this criterion, nuclear research reactors are classified into fast neutron reactors and thermal neutron reactors. To continue, it is important to pay your attention to the main types of applications of nuclear research reactors in the world. So this is the table which exemplifies the main applications and the number of reactors in the world involved in implementing, for example, teaching and training, activation analysis, or isotope production. You see the number of the research reactors varies in accordance with the appropriate application. And today, I will pay your attention to activation analysis, isotope production, on the example of our Tomsk Polytechnic University research reactor. One of the applications, as you have seen in the table, is isotope production. Isotopes could be produced for medical application, for industrial application, or, for example, for calibration of instruments and detectors. In accordance with specific application, being medical or industrial, several types of isotopes are produced. And you see the examples. For example, if for diagnostic medical purposes, we talk about technetium 99 or xenon, for example, 133. If for therapeutical application, we talk about lutetium, palladium, etc. If for palation purposes, we, for example, talk about the production of such isotopes as samarium 153, yttrium 90, and many, many others. To continue this issue of isotope production, it is important to mention that there must be some flux or power level requirements observed. For example, if you remember earlier, I mentioned one of the criteria in accordance with which nuclear research reactors are classified. And one of them was neutron flux density. And we distinguish such reactors as low flux reactors, medium flux reactors, and high flux reactors. This information would provide you with the idea that if the research reactor applies to low flux type, only short-lived radioisotopes could be produced, as sodium, for example, calcium, argon, etc. If we talk about medium flux reactor, such isotopes as cobalt-60, for example, molybdenum, etc., could be produced. And of course, if the neutron flux density is high enough, this allows producing the isotopes which are specified on this slide. And not only this choice is limited. Another application, apart from isotope production of the nuclear research reactor, is transmutation effect. One of the examples that you could see on the slide is gemstone colorization. For example, you could see the white color untreated stone, and finally we see the irradiated. Let's talk about the role of our nuclear research reactor. We have the special laboratory which is engaged, is totally involved into this, realization of this direction as gemstone colorization. They, for example, produce blue topaz, and blue color, and it could be used for industrial purposes. Following the requirements, the neutron flux must be observed. So from 50 to 100 hours of irradiation required to produce such kind of stones, color of stones, blue color. And the research reactor must operate on 2 megawatts power. To continue, another type of transmutation effect, which is also conducted at the TPU research reactor, is silicon transmutation doping. This slide demonstrates the isotopes of chemical elements which are used to conduct this research, and it's widely developing research in which many students, such as bachelor and master, and of course PhD students, are involved. And here we trace the connection of nuclear research activity, nuclear research facility, and the science produced by the students of the TPU. This is a kind of interdisciplinary approach. Another application, which was described and listed in the table several slides ahead, is food irradiation. My colleague from Moscow Nuclear Physics University talked much about different methods, different technologies, different experiments which are used on irradiation of water, wastewater, gaseous influence, and many other things. Food is also irradiated at the research reactor for a variety of purposes. First of all, food irradiation is a kind of direction which is aimed at processing of food products to control foodborne pathogens, to reduce microbial load and insect infestation. So, in other words, to get rid of all bacteria which inhibit the consumption of the food and selling them in the shop, for example, because we all want to buy fresh, good-looking fruit. Sometimes this is not possible, and food irradiation helps mankind a lot in this context. The major purpose, as I have already mentioned earlier, of irradiating food is to cause changes in living cells. This can either be the contaminating organisms to reduce pathogenic microorganisms or cells of the living foods to achieve their better quality. The biological effect of ionizing radiation is related to the size and complexity of the organism. The mechanism of action on cells is known to alter cell membrane structure, reduce enzyme activity, reduce nucleic and acid synthesis, and produce changes in cellular DNA composition. The results of a lot of research, radiation research, they have demonstrated that microorganisms that survive a dose of radiation are injured. Therefore, they are more vulnerable to the destructive effects of storage under conditions that are unfavorable to microbial growth, and they are more likely to be killed, for example, by cooking, as the picture at the bottom demonstrates. Another application of food irradiation is sprouting inhibition and ripening. For example, let's take potatoes. Sprouting of potatoes and many other vegetables can be also inhibited by irradiation in the dose range 20-150 grays. Radiation affects the biological properties of such products in such a way that sprouting is inhibited or completely prevented, and we could buy wonderful, good-looking, very much fresh potatoes. Another example is insect disinfestations. Insect disinfestation by radiation in just the dose range just from 0.2 up to 1 kg is aimed at preventing losses caused by insect pests in stored grains, in cereals, flour, coffee beans. So what we can consume and what we buy almost every day, at least several times a day. A minimum absorbed dose of about 150 grays can ensure security against various species of fruit flies and fresh fruits and vegetables. And in most cases, irradiation either kills or inhibits further development of different life cycle stages of insect pests. To continue, food irradiation also helps us to extend the shelf life of the products. For example, strawberries, which we could see on this slide, non-irradiated and irradiated. And these good-looking strawberries could be kept on the shelf of the shop just from maybe not 1 or 2 or 3 days. It can be prolonged up to even 1 week, owing to food irradiation. And in this case, a dose of 2.5 kilograms can extend the shelf of a chicken or a pork as much as a few weeks. And this is very much helpful, especially for the countries which are suffering from this problem. Spice irradiation is also an example of food irradiation, because we also like to have our food dishes spicy. We want them fresh so that they can be kept for a long period of time. And in this situation, and we know that spices are derived from plants, and that can be contaminated with microorganisms from the soil, and this problem needs to be eradicated. Of course, those of from 5 to 10 kilograms could bring satisfactory results, which means to eliminate bacteria, mold spores, and insects without negative, I would underline, negative impact on chemical or sensory properties, which is very much important. And this is a big advantage of food irradiation. I would underline again, food irradiation can be easily performed on the basis of nuclear research reactor facility in general, let's say so, facility. To continue this presentation, of course, it is worth mentioning some ideas on TPU's facilities equipment, which are used to conduct a variety, to implement a variety of applications. First of all, the TPU has nuclear research reactor, whose power capacity is 6 megawatts, laboratories which are located on the basis of this reactor, and these are clean rooms complex to produce radiopharmaceuticals, technological complex to produce radiopharmaceuticals based on technetium 99, technological complex for neutron capture therapy. We also have cyclotron complex, again for radiopharmaceuticals production, and cyclotron RM7. I will talk briefly about each of them during the next slide. If we talk about our reactor, research reactor, this is a pool type reactor, with the neutron reflector being beryllium. Moderator serves as light water. The flux requirements are demonstrated on the slide, and operating lifetime of this reactor is extended just to 2035, so it has enough time to operate, to do a lot of research. Main application fields, of course, they are not limited, but include the following ones. This is the development of technologies for obtaining new diagnostic and therapeutic radiopharmaceuticals. This is the development of neutron capture therapy methods for cancer treatment, nuclear transmutation doping of silicon, and radiation material science. And I would repeat again that all these applications are implemented not only by the laboratory staff members, but also with the involvement of the TPU students, master and PhD students. Nuclear research cyclotron, which is located very much close to this building, it has a number of characteristics, peculiar characteristics, which are demonstrated on the slide, such as it regulates the energy of accelerated particles. It accelerates varying ions ranging from hydrogen to argon. It has special channel for conducting neutron therapy to treat oncological patients, almost on the daily basis. The application fields include fundamental studies of the ions' interactions with matter, activation analysis of the elemental composition of substances and materials, as well as production of polymer membranes and metal nanostructures, and medical radiopharmaceuticals. Another type of nuclear research facilities is Betatron. And on the slide, you see the example of Betatron, which is manufactured in one of the laboratories based on the Tomsk Polytechnic University. Its design characteristics are presented on the slide, as well as main application fields, which include, and not limited to, film and digital radiography of welded joints and building structures, which is very much important nowadays, tomography of aerospace, shipping, and military equipment nodes, inspection complexes, for example, road transport or railway containers, sea containers. Betatrons are very much highly used, as well as in superficial radiation therapy or intraoperative radiation therapy. If we talk about the main purpose of all these facilities, which are available on the basis of Tomsk Polytechnic University, of course, it is important to say that a wide range of application is devoted to radiopharmaceuticals production based on radioactive isotopes, which are produced at these nuclear research facilities. And all this job that is being done daily is aimed at the diagnostics of various types of tumors, diagnostics of heart disease. And you know that in accordance with World Health Organization, these two types of diseases occupy the first positions in the number of deaths around the world. The first place is occupied by heart diseases. The second place is occupied by cancer. That's why the research, which is done daily, 24 hours a day, is aimed to help people survive or help people avoid or prevent them from having these tumors, because isotopes allow conducting diagnostics of cancer. Here the slide introduces the examples of the production of isotopes at the reactor, such as molybdenum, which transforms to technetium-99. And another example, cyclotron production of radiopharmaceuticals based on thallium-199 and iodine-123, production of these isotopes for cancer treatment. And as the concluding slides of this presentation, this would bring the information concerning the prospects, the perspectives of the development of nuclear medicine technologies, mainly, of course, if to refer to TPU. As I have already said, the nuclear medicine would continue production of isotopes for diagnostics and therapy, and these isotopes are listed on this slide, as well as interoperative radiation therapy. It is being highly developed nowadays because it has a lot of advantages in comparison with, for example, fractionated radiation therapy. It means that interoperative radiation therapy would replace the 5-week external radiation therapy. Just 1 minute of the therapy would help patients after surgery when their tumors has been eradicated. It would help as a method of further treatment. So 1 against 5 weeks training, 5 weeks treatment. Of course, this counts a lot for a patient because every day counts. So our laboratories are deeply involved into this kind of radiation therapy with the usage of nuclear research facilities. Neutron capture therapy is another prospect. Of course, it started a long time ago and is still under continuation because this is a unique technology for the treatment, this time inoperable tumors. So tumors which couldn't be operated and they are located in the head or neck. And neutron capture therapy allows treating the patients with severe tumors, you see, to survive this disease or sometimes to prolong their life for several years or sometimes even decades of years. Of course, the PU cannot conduct this research alone. We have a lot of partners, which are located also here, very much close to this environment where I am now. This is the Special National Research Medical Center specialists. These are Novosibirsk State University specialists. Novosibirsk, just 4 hours travel from Tomsk. So, but still, we work together to develop this trend, neutron capture therapy. And I would underline again that loads of students are involved in these processes to help scientists, researchers conduct these activities. Finally, my last slide demonstrates short information about bachelor and master nuclear degree, which any students in the world could obtain here and become a member part, you see, of our wonderful scientific and research team in the sphere of power and non-power application of nuclear energy. Our program, for example, master program, which is named as Nuclear Science and Technology, has several tracks in which students could be enrolled, such as nuclear power engineering for those who plan to continue their job career, to have developed their career with the operator of a nuclear reactor, nuclear medicine, the production of radiopharmaceuticals, neutron activation analysis, therapy, cancer and neutron analysis, etc. And those who are who wish to be engaged in nuclear security, safety, non-proliferation of nuclear materials are welcome to join our third track. We also conduct a variety of additional courses for different categories of specialists, not only for students. Their names are presented on this slide, and we would be very much happy to welcome everybody here as a part of our scientific team or as a student community member. Thank you very much for attention. It was a great pleasure for me to deliver this information to you. Thank you very much.
Thank you very much, Julia, for a very interesting topic about science and chemistry and future development of technologies. Now I would like to give a floor to the Mikhail Alexeyenko, Mr. Mikhail Alexeyenko, the first secretary of Embassy of Russian Federation on Philippines. As soon as we are translating our presentation for Asian countries, please.
Thank you so much. Thank you. Good afternoon, dear participants. I'm glad to welcome you to the online conference, Non-Power Nuclear Applications. Science doesn't stand still, and new methods of non-energy application of nuclear technologies appear in our arsenal. The conference will be devoted to their review. You will hear reports from the representatives, and you already heard of National Research Institute, Nuclear University MEPhI, and Tomsk Polytechnic University. And I can't stress enough the importance of getting an engineering education in this field of nuclear technologies, and note that Rosatom is a world technology leader. I'm also happy to announce that you have an opportunity to receive a quality education in one of the leading university in Russia under a quota, and of course it's for free. I hope you enjoyed the presentation and speeches. Thank you for their announcements and their time. And of course, this is more informational in nature, but I sure your all major accomplishments are built from the small steps and small tasks. Thank you for your participation and look forward to see you at more presentations, some projects, and our public meetings. Thank you so much. Thank you for time.
Thank you very much, Mr. Mikhail Alexeyenko, the representative on Russian Federation in Philippines. And I would like to remind our participants and future students who are interested in studying Russian that they can register on the website education-in-russia.com. And deadline on 15th of December. On this website, apply your document information. You can get a quota to study in Russian university for free. Thank you very much, everyone. It was pleased to provide this conference, and thank you for our speakers, Rosatom Corporation, our professors, and representatives of Russia. Thank you very much.
Thank you. Thank you.
Thank you so much. Thank you. Have a nice day.